Hello everyone. Welcome today to today's data learning talk. Today we're very happy to have Yuandong Tian from Meta, who is a world-renowned researcher in contrastive learning. Today he will talk about what better understanding of deep contrastive learning. Yuandong, the audience is all yours.
Okay, thanks everyone for attending this talk, and thanks for the invitation. So today I'm going to talk about the contrastive learning topic. The title is Towards Better Understanding of Deep Contrastive Learning. So I'm a research scientist and also a manager in Meta AI right now in FAIR. So this talk is mostly a little bit theoretical on basically understanding why contrastive learning could work and what is the internal mechanism inside it. So that's basically like a series of research directions that have been pursuing for years about understanding deep learnings. So we all know that deep learning has already achieved a very great empirical success, right? So from AlphaGo to AlphaStar to like different vision and language and speech and applications, right? And also DataE and recently ChatGPT. I think I didn't put ChatGPT images there. But that's definitely another way of search for AI, showing that AI, what kind of very impressive result we can achieve using artificial intelligence. That's very encouraging, and it's kind of unheard of given the history. Right, so one of the important components for artificial intelligence is right now is kind of like self-supervised learning. Right? So what is self-supervised learning is that instead of asking the humans to label data, we actually want the data to learn by itself. So one thing we can achieve that is that we basically say, okay, start with the entire data set, and then we get rid of some part of the data sets and ask the model to learn and to predict the missing piece, right? So that's actually a common theme provided by many existing works. So this range from vision or to NLP to speech, and also even for the ChatGPT, for GPT, you actually see like how they train model is that they just basically do very simple next word prediction, right? So do language model predictions. So this signals is actually turned out to be very powerful for training a model that can learn good representations. That's actually very surprising and also mysterious at the same time. Right? So I think the major theme of this talk is to understand how this kind of self-supervised learning approach works and how can we make it better. So in the talk, one of the topic I'm going to focus today is the contrastive learning topic. So for contrastive learning, usually what happens is that you have an image that comes from data sets, and that image or whatever modality of data, that data will basically go through different augmentations. Right, so it will basically go through different augmentations. For example, in that particular images, it can go through images, rotation, or scaling, or clipping. And then once you have the two images, xi and xi prime, and these two images will be sent to different neural networks. Right, so in contrastive learning, sometimes people basically send these two images to the same network with the same parameters, and then these two images are undergoing this contrastive loss. Okay, so that's a very simple framework. And after you train this model for many times, magically you will see good representations that emerges from the multi-layer network. Right? That's how it works. So here is basically like how the loss function was designed. That is called contrastive loss. So I just take this most famous contrastive loss called InfoNCE loss as one example. So here, what you want to do is want to minimize distance between the two representation of the same samples and the two different views, right? So here, you basically see, given sample I, it can go through two different data augmentations. And these two different data augmentations will give you two representations, Fi and Fi prime. You want these two distances to be as close as possible because you want the representation to be invariant to the distribution. On the other hand, if you have another sample J, and then what you want to do is you want to maximize the distance between Fi and Fj, which are the two representations of the two samples. Right? So these are called negative pairs, and you want to maximize distance. This is also reasonable because you want to actually get good representation so that it can distinguish between two samples. Right? So then you have these two different objective functions. Right? So in order to put them together, people have already discovered many different ways to put them together. So one example is, as I mentioned, the famous InfoNCE loss. You put these two distance, interview and intraview distance into these equations. And naturally, by minimizing these loss functions, you are simultaneously minimizing the probability path distance and maximizing the negative path distance. So this loss has been leveraged in many scenarios. Right. So I think for this talk, we're going to talk a little bit about this understanding of contrastive loss. So most of the work that is working on the contrastive loss understanding, usually they treat the neural network as a black box function approximator. So what that means is that you think this neural network as one function for a large family of the network, right? So of a large family of hypothesis space. And then once you have that, then you want to basically say, you want to show that you can pick one function, which is the trained model. That function is able to learn a good representation so that the downstream task is doing a very good job with this representation. Right. So in terms of the language of mathematics, what you want to actually prove is that the contrastive loss and the downstream classification loss has these following properties. Right. So you want to justify that if the contrastive loss is small, which is the goal of your pre-train or your self-supervised learning training, your downstream classification loss will also be small. So that's basically like how people usually prove things on the downstream tasks. However, if you check, there's actually additional term. There's the term called bound. The bound usually will depend on the complexity of the function family. So the larger the family you are considering, the looser the bound is, because there's just so many possible functions that can be chosen during the training. And the second is that there need to be assumption about relationships between the pre-training and the downstream tasks. Right. So, I mean, intuitively, you really want to think about like this pre-training has to be connected with downstream tasks in order to make these connections. Right. So these two loss functions should be bounded. If the pre-training has nothing to do with downstream tasks, then how come you can actually bound this? Okay. But actually, if you follow this line, there's actually not that. There's a lot of actually this kind of like the cases that is not following that kind of bound, or the bound is turned out to be vacacious, that's like too loose to be useful, right? So in order to understand what contrastive learning is doing, so my point of view is that we have to also think about what is the property that can be exploited by the neural network. Neural network is important. We cannot trust and treat neural network as a black box. So here's one counterexample that shows this bound may not be very useful. Right? So for example, here in this paper provided by InfoNCE and etc. and for Microsoft people, what they show is that there is counterexamples. Right? So they have shown their example for this special case that the contrastive loss function is close to each other. But their downstream task performance is actually very different. Right? So you basically construct this data set, and then you construct two functions, f and g, so that in this pre-training step, this f and g are having very similar loss functions. But in the downstream tasks, the g's loss is much larger than f's loss. Right? So which means that the contrastive learning may not be able to necessarily give you a good representation that is useful for downstream tasks. So it's actually a very interesting phenomena. So they also show this figure. That figure basically shows that So for the same contrastive loss, right? So for example, this one, you can construct two representation, two functions. One have very perfect downstream accuracy, 100%, and the other will have almost a random guess accuracy, right, which is 50%. And this is not only happening in the construction case, but actually, if you run different loss functions, if you run different optimizations, right? So if you try like different trials, then you got to see the same behaviors, right? So you basically see that you also see like with the same contrastive loss, right? The one that is trained with Adam is having a hard time getting good downstream results. But the one that is trained by ICG has reasonably good results, right? But if you train Adam plus weighted K, actually give you also good accuracies, right? So this basically shows that we are not only need to think about the structure of contrastive loss, but we also want to think about what is the role that is played by the neural network and by the optimizers. Okay. So this is actually very important. Because if you think about like why deep learning actually works better than the previous approaches, you will actually see that all these loss functions, they have already been proposed previously, actually is being leveraged in the previous literature. But the only difference between the models before deep learning era and after deep learning era is that we are using deep models. And what the secret is the deep model actually has that secret. So we really need to open the black box and study the deep models, right? So so basically here the principle is that we want to open the black box and we want to analyze the loss function and the architectures at the same time in order to get a good understandings of how the contrastive learning is working for the deep neural networks. That's why we call this top title as deep contrastive learning understandings, but not contrastive understanding. Okay, so let's start with this first paper, and this paper is an oral paper for last year's NeurIPS that tried to understand contrastive learning using the coordinate-wise optimizations. So for that paper, what we do is that we first construct a general loss functions. This function is in this following form. That loss function has two parameters, phi and phi. And these two are actually random functions. As long as these two functions are monotonously increasing, it will give you a contrastive loss. Okay, so people may wonder, okay, how large this contrastive loss family will cover. So actually, it will cover many different kind of contrastive losses. So here's one example for InfoNCE. So for InfoNCE, you start with these loss functions, but after some very simple algebraic manipulation, you're able to get this equivalent form. And that form, you see the phi defined as a log function and psi defined as exponential function. Right, so then we can conclude that the InfoNCE loss is part of that family. Okay, you can in the next step that we can see there's a big table that shows there are many different loss functions that fall into that family. Okay, so the main topic, the main point of view of this paper is to show that this minimizing contrastive loss, so basically this kind of contrastive loss optimization procedure is equivalent to the following coordinate-wise optimization. Right, so in that coordinate-wise optimization, what's happening is that you, instead of having just one parameter theta to optimize, you actually can discover two different family of parameters to be optimized. So first you have this max player theta that try to learn the representation to maximize the contrastiveness. So this ended function is another kind of form that can represent contrastiveness. So this is something that we are familiar with. We know all the contrastive laws are doing that. But after our analysis, we also discovered that there's another minimum player. That minimum player, yes, can be shown to minimize the contrastive loss subject to a regularization factor. Right? So the meaning of this mini player is to find distinct sample pairs that will have the same representation or very same representations. So this is basically hard negative pairs. Right? So this basically shows that the InfoNCE loss or many other loss that fall into this loss family are actually doing implicit adversarial discovery and adversarial learnings. Right? So, and this is basically the proof of it. So here we basically put a few sentences about what is that energy function, right? So the energy function is actually a different way of expressing contrastiveness. So instead of defining a loss function that is complicated, so in the energy function, that function actually has very clear and nice forms, and people can maybe able to use it. So it's a trace of a contrastive covariance. Right, so you have two f theta. So basically, f is the representation of the input x, and you take the contrastive covariance and you take a trace of it. That become your energy function. Right. So this is basically the figure that shows what are the contrastive losses that can be represented by this family. Right. So you have a phi and phi, which are the two functions that determine the loss functions. And for all the contrastive losses, they are actually part of it. That's actually quite interesting. So it can actually cover many things. And our framework actually shows that for all these different functions, they actually correspond to the same energy function. This energy function epsilon is not changed. But the only difference is that the minimum player is different. So the minimum player is actually operating at different structures, right? Why that's the case? Because the minimum player actually has one component, which is the R, right? So this different regularizer actually will determine how the minimum player alpha is behaving in this coordinate-wide optimization. Right? So then by doing that, you can unify many different loss functions together into the same framework and use that framework to understand what these contrastive loss functions are doing. So here is a slide to talk about how this minimum player is determined. So one theorem that we show is that if psi is an exponential function, then we can really show this alpha is the minimization of an energy function and regularization. And this regularization is, and also the feasible set of alpha is different. So, and the alpha can be defined in different feasible set, etc. And the regularization term is entropy terms. And it depends on different feasible set, you're going to have different alphas. And this is the difference of different contrastive losses. Yeah. Okay, here's one example that shows that for InfoNCE, you can actually directly compute the alpha. And the alpha actually will put more weights on on two pairs that will have small distance in their representations. Right, so which means that these two representations really need to be separated out from each other. And we put lots of weights there in order to emphasize that. Okay. So by the way, alpha is actually an n by n matrix that defines in this n samples in a batch. Okay. So once we have that understanding of the contrastive loss, then the next question is can we do better? Can we actually devise interesting algorithms on top of that? Right. So one thoughts that is actually natural of following this analysis is that here alpha is a minimization of the energy function with respect to regularization. Okay, but that's actually in some sense an indirect approach to define alpha. So instead, we have proposed this paired weighted CL called alpha CL. Alpha CL is actually instead think about different ways. Maybe we should get rid of the alpha altogether. We just say, okay, maybe alpha should be determined directly from the current function theta, current parameter of the network theta. Right. So because this will basically give you a broader family of alpha that can be tried in the contrastive loss functions, contrastive losses. Right. So previously alpha is constrained to be an argmin. But now alpha can be any functions of theta. So we actually expand the design space of the contrastive loss in a new dimension. Right, so we actually tried this in Cypher10 and STL10. And it shows that with alpha CL direct, it actually gives you a reasonable performance, slightly better than existing approaches. Right? And this alpha CR direct is by direct setting alpha ij as an exponential functions. Right? So this is actually very interesting, and we can just try that, and it actually just works quite well. Yeah. So we can also basically do this on more data sets and also different backbones of a neural network. And we show that the alpha CR direct is slightly better than this InfoNCE loss, in particular for the first 100 epochs, in which alpha CR seems to be faster in terms of RNC by like 2%. Okay, so once we have that framework, then we can basically like think about like different applications of that framework, right? So one application is that maybe we should find the best alpha for the performance. Maybe we should leverage these ideas to more applications, like for example, graph neural network, right? So on the other branch, we also want to leverage alpha CR for understanding the contrastive learnings, right? So we in the following, we're going to talk a little bit about the understanding component. First is the understanding of the alpha CR when the neural network is linear. And second is like understanding of alpha CR when the neural network is nonlinear. That's nonlinear component. And there will be more work following that. Okay, so first we want to basically give a study about like how the contrastive learning will behave if the network is linear. Right. So interestingly, in the deep linear case, when the alpha is fixed, so alpha is not changing over CDAS, it's a fixed parameter, then we can actually prove then the contrastive learning actually will reduce to PC objectives. So it's actually an interesting observation. So when the function, the network is actually a linear network, deep linear network, then we can prove the following theorem, that almost all local optima are global, and you can prove it's a PCA. In fact, there's a theorem 3 that tells you exactly the structure of the final solution of contrastive learning. So in this case, when you have multiple linear layers stacked around each other, you can prove that all the weights after convergence will become rank 1. Rank, this is basically an equivalent representation of rank 1. Right, and the optimal solution will basically be the max. This optimal solution will basically is the maximum eigenvector of the contrastive covariance matrix X of the input. Yeah, so in summary for this paper, we in the theoretic part we basically say that if we fix alpha and if theta is linear, then this will become a PCA. Right? So all these W's will become rank 1, and all this is basically a very simple simulation that shows this is indeed the case. Right? So the objective function will jump to the objective the PCA solution, and all the singular values, also the singular vectors, they are basically aligned with each other, so that all these W's rank 1, and all the singular vectors will be aligned with each other. So this is the previous conclusion is actually an extension of our previous paper published in ICLEAR 2022, right, in which we analyzed the dynamics collapsing issue in contrastive learning. So basically, like if you train a model with self-supervised learning using SSL, then we actually will see there's a lot of like collapsing issues for the contrastive learnings. We analyzed this for 1 layer and 2 layers in that paper, and in the neural paper we actually expand that theory to multi-layer neural network. Okay, so that's conclude the first part of the talk and also the first papers. So is there any questions? Okay, if there's no question, then I will continue. Okay, so in the second part of the talk, I'm going to talk about the follow-up work of this linear contrastive linear contrastive models. Right. So what happens if the network is nonlinear? That's one question of it. Right. So first of all, we want to analyze like what's the meaning of the constructive covariance C alpha. So this C alpha is people may wonder, okay, this actually from the representation from the mathematical expression, it looks like this will be very similar to the variance. There's actually a variance component here, right? So this looks like in some sense a variance structure. So indeed, you can show that the contrastive covariance C alpha is equivalent to the variance when there's some interesting conditions applied to alpha. So here's like one interesting theorem that shows when alpha satisfies these kernel-like structures. So basically, alpha can be computed as the kernel between the two augmented sample xi and x0i, x0j. In that case, then this when this number of samples in the batch goes to infinity, then this C alpha will converge to a summation of variance terms. Right? So that's basically the interesting property for the contrastive alpha here. And if there's no augmentation, then directly we get rid of this expectation term, and it will be G alpha. And then it will be basically like the variance of any function G. Okay, so that's basically just some analysis about the contrastive covariance. And the key problem here is that how can we understand contrastive learning when the multimodal is actually nonlinear, right? So we all know that the magic actually happens in the nonlinear network, right? And this paper is a follow-up of our previous AlphaCR paper. This paper actually got accepted in ICLR this year, so I haven't updated this yet. For this paper, we analyze both the one-layer and two-layer nonlinear networks. And we also assume there's a homogeneous activations on those two networks, right? So we basically assume that the activation function hx can be written down as h prime x times x, right? So this expression is actually satisfied in many activations. This includes the linear, ReLU, leaky ReLU, and also monomial activations with additional constant. So these are actually, especially ReLU and leaky ReLU, they are being leveraged in the real world neural networks. Okay, so for this paper, we also focus on mostly training dynamics as well as a critical point analysis. These include the statistics of local optima and also the dynamics of weights during the training. Yeah, so let's start with the one-layer nonlinear network. So suppose we only have one layer nonlinear network. So you have F theta, which is basically like a linear network, W transpose X, and H. H is basically the activation functions that is applied after this inner product. So with our framework, we can immediately write down the objective function of the contrastive learning applied to this one-layer nonlinear network, which is this way. So once we write it down, then by using the homogeneity property, we can actually take this W transpose out from the two and leaving like leaving this part here. Right? So here, this X titer is gated data points. So by gated data points, we mean that if that data point is within the activation region of the node, then that data point is active, and this gated data point equals to the original data point. But if the data point is out of the region of the activations, then we set this data point to be 0, literally at the origin. So once we have this definition, then we can write this down as the following form. So you can, if you can check like the structure, it's actually very similar to the PCA structures, right? So you still have W transpose A, W times A times W. So if A is constant, then this actually becomes PCA objectives. And the solution is obviously the maximum eigenvector of the A matrix. Right. So that's basically the difference. If you write them down, write the trend dynamics down, you should take derivative with respect to W, and you want to check like how the weights evolves over time. You actually can write. You can see this is actually very similar to the power iteration in the contrastive. In the power iteration for the matrix A, but this A right now actually changes over W. So this is the difference between this approach and the power iteration approach in computing eigenvectors of matrices. Yeah. So then, like you can see, there's actually a difference between linear and nonlinear networks in contrastive learning. In a linear network, when this A is a constant, right? So in that case, the A basically contains all the gated weights. If all the gated weights are constant because there's no gating, then we arrive at this constant A regime. In that case, the maximum eigenvector, there's only one maximum eigenvector for the figure. Right? So then the linear function is only converging to the single eigenvectors. However, in the nonlinear case, because A is now changing over different weight, so by having different orientation of W, you are able to create multiple largest eigenvectors at different dimensions. Right? So that's the key difference between linear network in the contrastive learning and nonlinear network in contrastive learning, at least in a single layer case. Yeah. Okay. Previously, we also analyzed basically the eigenvectors. These eigenvectors can be shown to be critical points of the original dynamics of the problems, but we all know that the critical point may not be equal to local optimum, because critical points are saddle points, and if you do actual training, you may escape from the saddle points. Right? You want to analyze that. We have a section in the paper that tries to define some auxiliary metric. One metric is local roughness. And if we show the local roughness is small and the gap between the two eigenvectors is large, then we can say this W star is actually stable, right? This is a local optimum. So then we analyze this local roughness metric for two loss functions. One is the uniform loss, and the other is the Gaussian loss. Right? So we actually show that this local roughness measurement is upper bounded by this structure, by this bound. And one part of this bound is actually depending on what are the alpha that are being used for the loss functions. And we show that this R is actually having interesting properties in which the upper bound of the roughness W in the Gaussian is much smaller than the upper bound of the roughness for uniform, right? Because the lower the upper bound is, the more easier for the condition to hold, right? And the condition basically says the gap of lambda needs to be larger than this rho. If this rho is smaller, then it's more likely that any stationary point become local optimum. So then this basically suggests that the Gaussian alpha is potentially having more local optimus compared to the uniform alphas. So this is also suggests that why this InfoNCE loss is having a better performance than the quadratic loss, right? Because if you have a more local optima, then you're able to save more patterns from the data, and these more patterns are useful for the representation of the network. Okay. So with the same analysis, we can also basically think about this multi-node nonlinear case. Right. As I said, in a single nonlinear case, because that there exists multiple patterns in the data, and therefore nonlinear network, the model can capture multiple local minimas, and each of them may correspond to local patterns. So if they have multiple nodes for this nonlinear network, we can actually show after the contrastive loss, the objective function that we want to optimize is basically a summation of independent one node objectives. Right? So this basically is original objective for one layer, one node case. And for multiple node case, you basically add all the independent one node objective together, one for each WK. So this basically shows the clear picture. Right? The picture basically says, even for multi-node non-linear network, if it's linear, then what happens is that even you have many different weights, they will all converge to the global maximum embedding eigenvectors because the objective function is basically an eigenvalue eigenvector problem. Right? So, and all the weights will converge to the same eigenvectors. And basically, you cannot capture rich structures in the data, and more nodes will not help. Right? But on the other hand, if you optimize a nonlinear model and a contrastive learning, at least in a single layer case, you're going to have multiple local optima eigenvectors. And each of them may capture a specific pattern in the data. And this specific pattern in the data will cover a different diversity in the data. And they will basically learn more patterns from it. This will make the representation much richer. Right. So that's basically the one of the big contribution of this paper, try to analyze what's going on with nonlinear network trained with contrastive learning. We then apply this idea to two-layer nonlinear networks, in which we also have multiple receptive fields, and also we have an additional layer that cover all the receptive fields. I don't want to go into too much detail about all the mathematical component, but I just want to talk a little bit about the idea that is being discovered from the analysis. So first of all, we want to have assumptions, right? The assumption basically says there's uniform alpha, a very large batch, and no augmentation, so that we can simply say V is actually C. So basically the variance, the contrastive variance become the variance. This will make the analysis easier. Right? So, and we also assume there's a fast training on the top layer, and also conditional independence given a hidden variable Z. So for the third condition, I will basically spend an additional slide to talk about that. So here we basically assume that exists and categorical variable Z, so that given the categorical variable, you can basically decompose the input X into multiple regions, and each region corresponds to basically a part of the input object. So that's basically the idea. And given this variable Z, which determines the overall shape of the object, I mean, each of the small component of the object can basically vary independently of each other. That's basically the very simple assumptions. Right? So you know that this Z is never being given in the training. It is not, it's basically hidden in the data. We know there exists some Z, and Z actually will help you in terms of like decompose the data. But we don't really have any kind of like supervision for the Z. Yeah. But interestingly, I mean, if you train the model with a deep neural network with contrastive loss, you might be able to discover the Z automatically from the analysis. So first of all, we basically show that the linear network cannot learn a lot of interesting features. Right? So if the network is linear, then we can actually prove they won't be able to learn any diverse features from this dynamics. But the nonlinear network, we're able to get rid of these constraints. And second, there's a fact called the global modulation. So in that modulation case, what's happening is that if you really write down the dynamics of the weights at case location, what you see is you still have this A here, which is basically this lower layer covariance matrix, right? But it will have an additional term. And that term is basically related to the hidden variable Z here. Right? And when you have a feature that is a distinctive feature for the hidden variable Z, in which like this data will be large because the feature will be different between z equals to 1 and z equals to 0, then you have additional term added to the dynamics, which basically will show that it will encourage the learning of the hidden features that can distinguish between the two hidden variables, z equals to 0 and z equal to 1, these two cases. So this basically shows that while this A can contain a lot of features as local maximum eigenvectors, these data can actually help the training to distinguish and to find features that really can decompose the data into multiple components. That's a very interesting conclusion. So, and this is basically shows that the details how this modulation could happen. I'm going to skip that. So basically, in conclusion, we see this trace interesting structure of this feature emergence, right? So doing the contrastive learning training, we don't need to specify anything about the latent hidden variables. We just put the data in and let it learn. But automatically, it will try to learn features that are sensitive to Z. So, and Z is in some sense a global structure. So it will try to learn some features, local features that is related to the global structure. And for feature that is not related to global structure or maybe just a local noise, they will be deprioritized during the training, which is actually a very interesting conclusion. So this actually shows that the neural network may automatically discover hidden variables and encourage learning of low-level supporting features that support the high-level concept. So this is actually very different if you compare this with Bayesian network. If you think about Bayesian network, all the hidden variables need to be specified beforehand. And then the task of machine learning is to estimate their conditional probabilities. Right? But the neural network do not need that. Sometimes like it will discover the hidden variables by itself rather than rely on humans to identify the hidden variables. And for the real world, usually there may be tens of thousands of hidden variables people never know. But it's going to be very hard for Bayesian network, for graphical network to actually discover all these variables. Okay, we also did some very simple analysis in the experiment setting to justify our theoretical findings. Right, so here we basically construct a very simple data set, and that data set is basically a string of tokens. Right, so we basically prepare a generator that can generate positive pairs and negative pairs, right? So each of generator will have a few like letters fixed, and for every location that marked with stars, it will basically be replaced by any symbols randomly, so that it can form an input sequence. Right? So for positive pairs, they are correspond to the same generator, but instantiated with different stars being in different alphabets. And for different samples, they will basically generated by different generators. That's how you construct positive negative pairs. And for each of the symbols, there will be an embedding for each of the symbols. Okay. So basically, that's how it is constructed. And there's actually for each of the generator, there's actually a way to construct that. Right, so for each generator, you're going to have some symbols being fixed. For example, in this generator, we have C, B, A, D, they are fixed at different locations. Right? So for different generator, these symbols can change. But for each region, for each position, there's only like a finite number of symbols being allowed to be used as a fixed symbol in the generator. Right? For example, for location R2, so 0, 1, 2, this is the third location starting from 0. And then in this location, we only allow to use A, B, and C symbols as the fixed symbol of the generator. Right? So then for that particular location, you basically will see these two symbols are basically relevant fitting symbols that can be useful for determining which generator it is. And there are 3 other symbols, D, and F. They are only be used when you are generating the actual sequence. So basically, these 3 are basically defined as irrelevant symbols that is only generated by wildcards. So in the training, we want to see whether we only learn like the symbol that would be useful for determined generators, which is basically the training set, the input, basically the underlying symbols, the underlying data points. So we train this with this two-layer networks architecture, and basically compute like whether the learn weights is matched with a token embedding. Right? So if these two are very close to each other, then we show that we can reconstruct the token embedding from the data. And the overall metric will be an average of all these matching scores. The higher, the better. So then we show that, interestingly, if first of all, if there's only like there's no diverse symbols and there's no overparameterization, then linear network is actually better than random network. Because linear cannot learn the diverse symbols, but when there's only one symbol, one patterns, linear actually are doing much better. So, but on the other hand, if there are like diverse relevant patterns, for example, at each location, there are 3 allowable patterns that can appear in different generators, then definitely you see that the linear is not doing well, as well as sigmoid, but these 3 leaky ReLU, and also ReLU, leaky ReLU, and the quadratic. These 3 are actually doing much better than other things. Interestingly, these 3 actually the homogeneous activation functions. Yeah, and we also compute the minus, which is basically irrelevant matching score. We want that to be as low as possible. And we show that ReLU has smallest minimal irrelevant matching scores. And here's a visualization about like what kind of feature it learns. Right, so then you see that for each of the image, each image represents one of the receptive field, right? So from R0 all the way to R9, because we have 10 different locations. For ReLU, it actually clearly shows that each of the basically like each of these activations, each of these weights actually capture only one single patterns, right? So it's very clear. And for patterns, that is for basically embedding that is not in the relevant set, none of the activations actually capture that. And none of the weights actually capture that. Right? So you see these clear patterns. But on linear setting, I mean, things are becoming really complicated, and we don't know how to interpret that. So we also test whether the quadratic loss has any advantage over the InfoNCE or vice versa. So we'll see that the quadratic loss actually has very clear patterns as very similar to the InfoNCE loss, but for the performance is a bit worse. Right, so this basically shows that our analysis can apply to different loss functions, because in our case, we basically use the framework of an alpha CR, and the alpha CR can cover both the InfoNCE loss and the quadratic loss. And the summary, so in this talk, I'm basically talk about the alpha CR framework. We first talk about how we convert the minimization of various contrastive loss functions into the alpha CR framework. And then we talk about its application as well as the understanding of alpha CR in both the linear settings and the nonlinear settings. So as a future work, one thing that I just mentioned is that this analysis actually show there could be a potential advantage of the neural network over traditional graphical models or Bayesian networks. So in that case, like the neural network may be able to discover automatically novel random variables, at least in two-layer case, while the graphic model can only operate on human-defined random variables. So in the future, we also want to analyze understanding and analyze other architectures with the training dynamics tools. This might, for example, include the self-attention and transformers, which are being super popular in recent work in different scenarios, including computer vision and natural language processing. Right. So the long-term goal definitely is that how to move towards a unified mechanism that can encourage feature emergence, which I believe is the key why neural network can be super successful in the empirical settings. Okay, thanks. This is my talk. Let me know if you have more questions and thoughts.
Yeah, thank you, Yuandong, for the nice, impressive, and also I found very theoretical talk. So for the audience, in case if you have any questions, please do not hesitate. You can either raise your hands or you can type your questions in the chat. So first I see Yuan, please go ahead.
Yeah, thank you for your presentation. So I'm wondering, like, how do you prove the effectiveness of this representation from this pre-training procedure onto these downstream tasks? So yeah. I don't know. Yeah.
Yeah, I think that's a good question. In this paper, we don't do that yet because the analysis is more on how the feature is learned during the pre-training process. Right. So basically, like if you want to prove further that this pre-training will lead to good downstream tasks, then you probably need to assume the downstream task will also use the feature that is learned by the pre-training step. Right. So once you have the assumption, then you can definitely prove some interesting bound. Right. But I feel like we should definitely understand the feature learning procedure first. Then we can assume that feature is being leveraged in downstream tasks.
Okay, thank you. So previously in the part one, like you said, the contrastive learning already exists, but the deep contrastive learning that is which really makes it powerful. But how is that? Like yes. You didn't discuss when the depth of this neural network goes larger.
I think here in this talk, we discussed when the depth it goes larger, for example, the deep linear network, and also the nonlinear network, right? So what are the features it is learned from data, right? So once we know what the feature it is learned, then if you want to analyze why this will apply to downstream tasks, you can always assume this feature is what the downstream task would like to use. Then you can prove the generalization bound.
Oh yeah. Thank you.
Right. I feel like generalization bound is not the key. The key is how we should and how we can understand the feature being learned.
Okay. So I'm wondering if your solution, your conclusion could apply to other forms of self-supervised, like non-contrastive ones, like GPT and BERT.
Yeah. So for non-contrastiveness, we actually had another paper in last year's, the previous year, so 2021, about of the BYOL, right? So but still, I mean, if you want to analyze BERT or analyze GPT, there's more work to do. Yes, not that applicable, but there's something in common.
Okay, thank you.
Thanks.
Yeah, thank you, Pengyan and Yuandong. So please go ahead.
Hello.
There's an echo.
Sorry about that. Hi. Okay. Hello. So thanks for your talk. And I just have one question at your slides start. So you said in the strong argumentation, the contrastive learning will converge to low rank latent space. So is it any beneficial if we can get the full rank latent space?
Yeah, I think first of all, this conclusion holds when the network is linear, right? So you have a linear network, then you can prove the contrastive learning will converge to low rank structures, right? So that's the conclusion precisely. Right. So in order to, for example, learn full rank structure, you probably want to add non-narratives. The narratives will help you capturing a diverse set of features. Right. So that's the first conclusion you can draw from these talks. Right. And second, for linear network, even if you want it to be high rank, there's no basically it's very hard to. I mean, even if you have a over parameterization. Yeah, the training will also collapse into low rank because there's really nothing you can learn with the linear structure. right? So basically linear structure will have this unity all kind of structures. So any direction that is slightly stronger than the other, all the weights will come to it. So you won't be able to learn diverse structures. But if you put like nonlinear activations, then this nonlinear activation will help you in learning more diverse features. And
so
hopefully this will be a low. This won't be that low rank.
Okay, so but can I consider it as a higher rank latent space will give us a more rich representation in the nonlinear stage?
Yes. I think so. You can think that way.
Okay. Thanks.
Yeah.
Okay. Thank you, Cho, for the question. So I think here's already 5:02. So just to see if there's any final questions from the audience. Yeah. So if not, I would like just to
Looks like there's more questions.
Oh, maybe I just had a very quick one. Thank you for the talk. It was very enjoyable. I just had Hinton, I think, recently pointed at the importance of like negative pairs. And without these negative pairs, even for like Bootstrap your own latents paper, you just end up modeling the dynamics of the network. For you moving forward, how important are negative pairs for contrastive learning?
Yeah, I think it's always like a very important for contrastive learning, right? So that's actually like one of the key part to make it work. I mean, even for non-contrastive learning, I mean, our analysis also show there's an implicit threshold that is determined by the weight decay, and that threshold will distinguish between positive pair and negative pairs. Yeah, so this is actually also very interesting. So even like the method for non-contrastive learning, there's actually implicit negative pairs somewhere, right, that is hidden in the training stage. Yeah. So and also, for example, for BERT or for any kind or other regressive models, right? So BERT or maybe like GPT-3, what they do is instead of like in order to predict some token that is missing, you are using, for example, softmax loss, right? And that softmax is also contrastive because you want to maximize the probability of that token and minimize the probability of the rest of tokens. So there's also a contrastive there in order to learn good representation and the features. So it's actually everywhere. So sometimes like the title of the paper try to make you surprised, but actually it's always hidden at some point.
Thank you. That's great.
Yeah, thank you, Harry. Let's see if there's no more questions. I would like just to thank again Yuandong for accepting our invitation and for giving such a nice talk. And thank you for the audience for joining us, and looking forward to seeing you in our data learning talk next week. So I would say good evening to everyone in Europe, and have a nice day, Yuandong. Thank you again for joining us.
Oh,
bye.
Bye.